Hello, everybody. Welcome to session 19 on 3D user interfaces, navigation, and flying teleportation. I'm the session chair, Gudrun Klinke from the Technical University of Munich in Germany, and let's get started. Have a few seconds to switch to the slides. The first talk will be on teleporting through virtual environments, effects of path scale and environment scale on spatial updating. This is a paper presented by Jonathan Kelly, Alec Ostrander, Alex Slim, Lucia Cherub, and Stephen Gilbert, all from Iowa State University, and it will be presented by Jonathan Kelly. He is an associate professor in psychology and human-computer interaction at Iowa State University, and he uses spatial cognitive theories to better understand and improve upon user experiences in virtual environments. It's all yours.
Great. Thank you for the introduction and for taking care of my acknowledgements of my collaborators at Iowa State University. I'd also like to acknowledge funding through the Cyber Human Systems Program at the National Science Foundation. So I'm going to begin by asking you in a moment to close your eyes and imagine walking along a path that I'll describe to you. And then at the end of the path, I'll ask you to point back to the beginning of the path origin. So for just a moment, please close your eyes. Imagine that the space around you is free of obstacles and boundaries. And imagine walking forward 10 feet or 3 meters. And now imagine turning to your right 90 degrees. And now imagine walking forward another 10 feet or 3 meters. And that's the end of your path. So now what I'd like you to do is to point back to the beginning of your path, the path origin. Now I can't see how well you did on this, but I can tell you that the correct answer is up here on the screen now. The correct answer would be to point back and to your right. In demonstrations like this, typically about half of people point in the correct direction and the other half point in the wrong direction. And often that's back and to the left, but it can be other directions as well. Now, if I had had you actually get up and physically walk this path, even with eyes closed, nobody would point in the wrong direction. And even those of you who pointed in the correct direction would still find it easier upon real walking. And the reason that it's easier when really walking is that self-motion cues are available from the body, from vision. Now I'm going to get back to those self-motion cues in a bit. For now, I want to point out that this is an example of a triangle completion task. And triangle completion is a measure of a spatial cognitive process called spatial updating. That's the process of keeping track of your position and orientation over time during self-motion. Now, teleporting has become one of the primary locomotion interfaces for moving through virtual environments. In this video, this shows the most common implementation of the teleporting interface. Here, the user selects a position in the environment to be teleported to, and then is instantly transported to that position. But to rotate through the environment, the user turns the body and gets visual self-motion cues as well associated with rotation. So changes in position, that is translations, changes in position are unaccompanied by any self-motion cues, whereas rotations are accompanied by the whole host of self-motion cues you normally get in the real world. So we call this particular interface partially concordant teleporting. And we call it that because rotations through the environment are in agreement with self-motion cues generated by those rotations, the body and the visual self-motion cues. Whereas translations through the environment, change in position, are unaccompanied by any self-motion cues. And I want to contrast that with another variety of the teleporting interface. We call this discordant teleporting. Here the user selects both a position and an orientation in the environment to be transported to. Now the user can still turn the head and body to look around, but there are no self-motion cues associated with navigationally relevant movements in the environment. So we call this discordant teleporting because now movements through the environment, translations and rotations, are completely unaccompanied by self-motion cues. So your body and your visual system is saying you haven't moved at all. Now, discordant teleporting is particularly useful for those who want to experience virtual reality from a seated position, especially from, say a fixed seated position like a couch instead of a swivel chair. So teleporting reduces cyber sickness compared to joystick interfaces. That's probably their main advantage. Um, However, teleporting has spatial cognitive consequences. The lack of translational and rotational self-motion cues when teleporting leads to larger triangle completion errors, so larger errors in the spatial updating process. However, research on spatial cognitive costs of teleporting has only tested small-scale movements in small virtual environments, whereas teleporting is typically used over medium to large distances. So in this project, we asked, do the spatial cognitive costs of teleporting generalize across manipulations of path size and manipulations of environment size? So we compared small versus large triangles, and we also compared small versus large surrounding virtual environments. Um, we pre-registered our experiment and shared data on the Open Science Framework. There were 32 participants in a fully repeated measures within participants design. Each participant completed several trials of a triangle completion task in which they traveled along an outbound path and then from the end of the path pointed back to the path origin. So just like the imagined example you experienced. The outbound path was marked by a sequence of posts, a green post, then a yellow post, then a red post. And at the base of each post was an arrow, and the arrow pointed in the direction of the next post in the sequence. Now, this was critical for the discordant teleporting interface, where the user selects both position and orientation. But for consistency, that arrow was included, those arrows were included across all conditions. So as I said on the previous slide, we manipulated the size of the path, we manipulated the size of the surrounding environment, and we also manipulated the locomotion interface. So it could either be partially concordant teleporting, where they rotate the body, or discordant teleporting, where there are no rotational cues. So fundamentally, that's a manipulation of the availability of rotational self-motion cues. We would have also liked to have included a walking condition so we could evaluate the contribution of translational self-motion cues, but for space reasons, we were unable to include that with large triangles. And then we measured the participant's response location in a triangle completion task. So this is an overhead view of the stimuli we used. The small triangles were about 1.5 meters per path leg, so 1.5 meters in length per leg. The large triangles were about 6.5 meters per path leg. Um, you can see the boundaries of the surrounding virtual environments. They were both square virtual environments. The small virtual environment isn't in fact all that small, but it's smaller than the large virtual environment. And I'll give you a little more detail on what those look like now. So this is a perspective view of the small virtual environment. It was a warehouse with landmark objects, but all the landmarks were pushed up against the boundaries of the warehouse. So there were no landmarks in the center of the space where the participant actually moved when doing the task. You can also see in this image a green post indicating the start of the path. That's the path origin. And at the base of the post is a light blue arrow pointing in the direction of the yellow post that you'll see next, marking the first leg of the path. So this is a video showing a large triangle trial using the partially concordant teleporting interface. So the participant teleports to the green post. That's the beginning of the path, and it disappears. They then teleport to the yellow post, marking the end of the first leg, and then the red post, marking the end of the path. And then they turn to face the path origin and use this laser pointer to indicate where they believe the path origin is, the location of the green post. This is a perspective view of the large virtual environment. It's twice the size. It's also a warehouse. Objects are pushed up against the boundaries still. And this video will also show another example of a large triangle trial, but this time with the discordant teleporting interface. So now they're teleporting to choose their position and their orientation. So now the arrows on the base of the posts are particularly important. So they position and orient this purple triangle to match the position and orientation indicated by the marker, the post. So there are no self-motion cues on the outbound path, but when they get to the end of the path, they do turn to face, that is, they rotate their body and get visual information as they turn to face the path origin to respond. So in this case, the responses are equivalent across the interfaces. The only thing that varies is the experience of self-motion on the outbound path. I'm going to show you data now in terms of absolute distance error. This is the absolute distance between the response location and the correct location. So here are absolute distance errors on the y-axis. Green bars represent errors in the discordant teleporting interface. Blue bars represent errors in the partially concordant teleporting interface. And then the 4 pairs of bars represent the manipulations of path size and virtual environment size. Now, the first thing I want to point out is that in all 4 pairs, the green bars are taller than the blue bars. So errors are larger with discordant teleporting than with partially concordant teleporting. So those rotational self-motion cues matter for spatial updating. The other thing I'd like to point out is that larger paths produce larger errors than do small paths. So if we look here in the small virtual environment, the large path, the large triangles, produce larger errors than do the small triangles. Likewise, over here in the large virtual environment on the right, large triangles produce larger errors than do small triangles. And this effect of path size is exaggerated in the large environment compared to the small virtual environment. So I want to dig into this a little more deeply, but before I do that, we need to put the large and small path data on more equal footing. And what I mean by that is if you can imagine, so the large paths involve pointing longer distances. So if you imagine taking a laser pointer and pointing across the room versus at something close, small angular changes in your arm position are going to have larger positional consequences for the far target than for the near target. So to put large and small path data on more equal footing, I'm going to next show you the data in terms of absolute angular error. That's the absolute difference in degrees between the response direction and the correct direction. So it ignores the distance component of the response and focuses only on the angular component. So here are those data, absolute angular errors on the y-axis. One nice thing about looking at absolute angular error is that I can tell you chance performance is 90 degrees, and all the bars are well below 90 degrees. Just like before, we see green bars are taller than blue bars, indicating that discordant teleporting produces larger errors than partially concordant teleporting. And the thing that stands out now, in my opinion at least, is that 3 of the pairs of bars look almost identical to each other. And the only pair that looks unique is this pair over here representing data from large triangles in the small virtual environment, where errors are lower overall and the difference between interfaces is smaller. So why is that? We believe that it's because that it has to do with the proximity of landmarks. So this is an image from a large triangle in the small virtual environment. You can see landmarks are pretty close to the path origin. And if you look over on the right in the schematic view, the start and the end of the path brings the user pretty close to the boundaries of the path, where the boundaries of the environment where the landmarks are. Whereas small triangles, which were also more or less centered in the environment, keep the participant pretty far from the boundaries and the landmarks. In the large virtual environment, it doesn't much matter which path we're looking at. They all stay pretty far away from the boundaries where the landmarks are located. So going back to the data, the large path data, large triangles in the small environment produce lower errors because nearby landmarks enable landmark-based navigation. Another word for that is piloting, landmark-based navigation. Whereas in the other three conditions, participants rely more heavily on path-based information and less on landmark-based information. So I began with the question, do spatial cognitive costs of teleporting generalize across manipulations of path size and environment size? And the answer is clearly yes. Rotational self-motion cues improved triangle completion performance under all tested conditions. So the green bars were always higher than the blue bars. I'd like to be able to say something about translational self-motion cues, but we didn't have a walking condition where those were available. The best I can do is refer back to some work we've done with small triangles, where translational self-motion cues do seem to help, in addition to rotational cues. Furthermore, nearby landmarks enabled piloting, that is landmark-based navigation, which led to more accurate performance and reduced the difference between the two interfaces. So in other words, it reduced the consequences of removing the rotational self-motion cues. So a couple of closing messages for designers of virtual environments. We recommend avoiding discordant teleporting when possible, providing as many self-motion cues as can be made available. Furthermore, we recommend including nearby landmarks so as to increase navigational precision by allowing piloting and reducing reliance purely on path-based information. And thank you.
Okay, thank you very much for your presentation, John. That was very exciting and interesting. We have already a few questions lined up on Slido, and for everybody out there, please send us your questions so I can post them to the speaker now. There's one by Eric Hodgson saying, why did users have to teleport to the first post instead of starting in their current position? Does the extra teleportation hop add extra error?
That's a good question, right? So every trial started by showing the participant the green post and then having them teleport to that, which then kind of began the trial. Another approach would be just to start them at the green post. And our rationale for that was that we found that allowing participants to view the green post from kind of a third-person perspective, particularly in the context of the landmarks, allowed them to better encode its position than simply starting them there. It's possible that adding that extra teleportation hop added additional error, but we think that the addition of any potential addition of error in doing that was offset by being able to see the post from that third-person view. Yeah, thanks, Eric.
Okay, there's another question by Bernhard Ricke about saying, did you check how do the errors compare to physical walking conditions or continuous virtual locomotion? That is, any idea if teleporting increases error?
Great. Thanks for that question, Bernie. So in terms of walking, we didn't include a walking condition in this particular experiment because the large triangles were prohibitively large for our physical space. We've included that walking condition for some smaller triangles we've done in other studies. And certainly participants do better with walking than they do with simply teleporting and rotating. So better with walking than with partially concordant teleporting. We haven't included the other condition you mentioned, which is just continuous virtual locomotion. And that'd be an interesting one to include in this. My prediction is that it would fall somewhere in between walking and partially concordant teleporting.
Okay, well, thanks for the questions. Keep them coming. I think we have to go on to the next presentation due to timing limitations. But also let's meet in the hub after in a hub after the session is over, and then we should discuss all these questions and also have discussions in our Slack room together. So let's continue with the next presentation. We'll have a few seconds of interruption before the next presentation starts. Okay, our second presentation is on the topic of getting there together, group navigation in distributed virtual environments. It's by people from the Bauhaus University Weimar in Germany, by Tim Weisker, Pauline Bimberg, and Bernd Fröhlich. And Tim Weisker will give the presentation. He's a PhD student working in VR and visualization research. And his research interests include interaction techniques, multi-user VR systems, HMD installations for multiple co-located and remote user groups. It's all yours, Tim.
Thank you very much for coming, and welcome to the presentation of our paper on group navigation in distributed virtual environments.
We're supposed to see a video
group
now,
navigation is a process that is quite
Oh,
common
yeah.
in the real world, because in order to get somewhere together, it's usually more efficient to use a shared vehicle rather than going there one by one. This is especially true when the points of interests are difficult to reach, or if you just have one tour guide in the group knowing how to get to these points of interest. In virtual reality, group navigation can also be used to ensure spatial consistency among co-located users, meaning that if you consider these users to be on the same movement platform, or magic carpet if you like, then by moving this platform around we can ensure that the virtual avatars of these users will always align with their real-world positions in the physical space. And this is quite nice because then spoken words will always come from the correct direction of the virtual avatars. And also when walking around on the platform, users can easily ensure that they do not just bump into each other. And this setup here is now very similar to that tour bus in the real world, where multiple users can travel together through the environment and experience something together. And last year at this conference, we presented a group navigation technique that supports exactly this scenario for two co-located users. And this technique is called as a result, users
No,
it's
great.
navigate individually.
For me.
Okay.
But what happens
Okay.
now if a second
All right.
user joins me? Hi. Hi. Now,
Okay,
if we
I'll
want to get
unmute
somewhere
myself here
together,
again to listen.
both of
I
us
hear
have to
some
provide navigational
in the
inputs.
Twitch.
So let's assume we would like to go over there. Then my colleague behind me has to perform very similar inputs to get to the same destination. And one could argue that this is a little redundant and could be optimized in a way, especially when the second user doesn't even know where I would like to go to. And as a result, we believe that group navigation techniques can also be very beneficial for distributed users and not only for co-located ones. So in this paper, we present a framework for group navigation techniques that is based on the observations of the social psychologist Bruce Tuckman. And he observed that groups working together typically undergo a sequence of developmental stages when working together. And we claim that the very same is true for group navigation. So successful implementations of group navigation must provide mechanisms in each of these four phases. First, forming mechanisms allow users in the virtual environment to create a group, so to give consent that they would like to switch from individual to group navigation. So for example, a high five gesture. Afterwards, the actual process of getting somewhere together is an interplay of norming and performing techniques, when norming relates to distributing responsibilities for group navigation, so specifying who's the navigator of the group at which point in time. Now this could be me, for example. Go ahead. And afterwards, performing techniques allow the designated navigator to generate the displacements of the whole group through the virtual environment. And we cannot show it right now because it's not implemented here in Mozilla Hubs. And finally, once joint work is done, users need adjourning mechanisms that allow them to switch back from group to individual navigation. So to dissolve the group. Bye.
Bye.
So as there are no implementations of group navigation in distributed virtual environments up to this point, we wanted to go ahead, and our first idea was to take the multi-rate jumping technique that was originally developed for collocated users and just apply it in the performing phase of two distributed users navigating together. And while we did that with some pilot testers, we observed one major difficulty. And this is illustrated in this video, where we have two users navigating together. Everything's fine up to this point, but once they physically rotate their bodies at corners in the environment, their spatial formation also changes. So before it was a side-by-side formation, and now it's a queue formation, so users standing behind each other. And if this is undesired, again, they have to coordinate verbally and move in their individual tracking spaces to correct that before going on. And they have to do it at every corner in the environment. And while we acknowledge that this might be unavoidable in collocated setups, because we have this shared physical space that just tells us how we have to place the avatars in the virtual environment, we believe that we can be more flexible in distributed virtual environments. And in this paper, we present an extension for multi-rate jumping, which we call multi-rate jumping with virtual formation adjustments. And the idea of virtual formation adjustments is that users do not have to physically walk anymore to adjust their formations. So let's see how this works. We have the navigator of the group here planning a jump, and this is the controller of the navigator over there. And the idea now is that while planning a jump, by swiping on the touchpad, the navigator can just specify where they would like the passenger to end up. And again, the pink gray here is just a visual feedback of the navigator's intentions. Once they are satisfied, the formation adjustment is just directly included in that jump. And while this certainly reduces the amount of physical walking, we were unsure if such a technique would be really well received by real users of such a system, because it places a lot of additional responsibilities on the navigator, while the passenger has just simply to look around and understand what is going on. So in order to investigate this in more detail, we conducted two user studies, where the first study was a quantitative evaluation of our technique, where we only focused on the performing phase while isolating all potential confounders that might occur in the other phases. And afterwards, we conducted a qualitative expert review in a more realistic scenario, where we really implemented the full chain of stages from forming to adjourning, and just wanted to find out if people would really voluntarily switch to group navigation, and if they would voluntarily use our technique for generating virtual formation adjustments. So in our first study, we invited 20 user pairs without additional backgrounds of VR systems. And in this study, we decided to focus on transitions between side-by-side and queue formations. Because, as you've seen in the video earlier, these formations can occur quite often when we have turns of 90 degrees in the virtual environment. And as independent variables in this study, we compared the regular version of multi-rate jumping as the baseline to the version of multi-rate jumping with virtual formation adjustments included, which was the adjust condition. And our task was rather simple. It involved users standing in a certain start formation to perform a jump and to also adjust their formation to a different target formation. So in this example, they should transition from a side-by-side to a queue formation. But of course, across multiple trials in this study, we varied both the start formation and the target formation, as well as the interpersonal distances of both users. So in the baseline condition, they could just perform a jump, but they had to adjust their formation by physical walking. And in the adjust condition, the navigator could just include the formation adjustment to that jump. Our two main dependent variables were the task completion times and the task loads that were generated for the navigator and the passenger. And we used the NASA TLX questionnaire to measure that. And when looking at our results, we could indeed confirm significant advantages of the adjust condition in terms of task completion times. And we could also confirm significant advantages of the adjust condition in terms of task load for both the passenger and the navigator. And for the navigator, this was a very interesting result because, as mentioned earlier, the navigator had more work to do in the adjust condition, yet the task loads that were generated for navigators were significantly smaller. And this is a very strong indication that adjusting formations by physical walking really seems to be demanding and should probably be avoided when navigating together. So overall, very promising results for virtual formation adjustments being included right in that performing technique. But of course, our study was also a little bit limited in a way that the scenario was rather controlled because the system just dictated users which jumps and formation adjustments they had to perform. And also our focus on side-by-side and queue formations was maybe a little limiting because it didn't cover like all the potential formations that two users might have. So we decided to go on and conducted a qualitative expert review in which we invited 12 VR experts, again in pairs, with additional backgrounds in computer science, civil engineering, and architecture. And the study took place in this pretty environment we're standing in here right now. And we briefed each user of such a pair about certain interesting features and anecdotes within this virtual environment. So one feature was, for example, hidden in the church behind me, and another feature was this pretty picture of an octopus that you see in the treehouse next to me. And another one was hidden here in the supermarket behind me. And then the task of these users was to meet in this environment and to just show each other around and explain to each other what they know about this environment. So this is quite a classic scenario where different users with different knowledge backgrounds meet in VR and just want to exchange about their interests and knowledge. And in order to complete this task, users could freely choose between individual and group navigation. So individual navigation looked like this. And to form a group, users could just hold their controllers together. That was the forming mechanism. And then just the first user to activate the target specification ray here automatically became the navigator of the group. Here it's the user in red, performing a jump without a formation adjustment. Now this user performs a jump with a formation adjustment because they both would like to end up in front of this car. Now they can discuss about it. And now the other user in blue takes over the navigator role and again performs a jump with a formation adjustment because they want the group to end up right next to that black car. Again, they can discuss, and once they were satisfied with working together, they could press a button on their controller to adjourn, so to split up, and to continue navigating individually. And from this scenario here, in this pretty environment, we measured the verbal communication channel of both users. We measured, of course, all their tracking data and inputs. And we also conducted some post-hoc interviews in which we focused on navigational strategies. And our results can be summarized as follows. We observed that all participants used mixtures of individual and group navigation to solve this task, where individual navigation afforded a very fast-paced input sequence, which was mainly used to get a very fast overview of certain parts of the environment, before coming back together and switching to group navigation. And group navigation allowed these users to stay together, to focus their verbal communications more on the content rather than navigational instructions. And also our feature for virtual formation adjustments here was heavily used, mainly to optimize the placement of the group with respect to certain features of interest, and also to resolve these undesired formation changes that occur when we have physical rotations. So overall, from this we conclude that successful collaborative work in distributed virtual environments really seems to benefit from fluent transitions between individual and group navigation. And as a result, forming and adjourning mechanisms should be especially easy and lightweight to use. So the takeaway messages from my talk today are that group navigation really seems to be an essential feature for collaboration in distributed virtual environments. That is, however, not implemented in the systems that we know about. And our framework here provides some guidance on how future developers could realize group navigation and which mechanisms are needed in particular to implement successful group navigation techniques. And in particular, we would like to highlight that it really seems to make sense to incorporate virtual formation adjustments to the performing phase of group navigation, because as we've seen today, they can make the group navigation process way more efficient and comfortable, just instead of asking users to adjust their formation by physical walking every time. So the big question now is, what's next? Next, we can perform technique developments and user studies in all 4 phases of the joint navigation process. And in the long run, we would like to aim for scalable group navigation techniques that allow more than 2 users to get somewhere together. And with this vision, I would like to conclude my talk for today, and thank you very much for your attention.
Okay, well, thanks a lot for this really exciting presentation done in a hub, which is a good advertisement for us to go to the hub afterwards.
Thank you.
And now there are quite a few questions that came up in Slido. I'll start with one by Doug Bowman. Instead of specifying where the passenger should end up, did you consider having the navigator specify which direction he wanted to face and then adjust the formation automatically to keep their relative positions after the jump?
Yeah, that's a great question. It relates to a lot of alternative versions on how performing techniques could work. Actually, this question goes quite well with the talk that we heard previously that talked about discordant teleportation that involves rotating the user. And yes, this talk and previous work has shown that this might impair the spatial awareness of users. So in this particular paper, we decided to go ahead and only consider the offsets for the virtual formation adjustments. But in the paper, it's like described as a concept that, of course, like changing orientations is also an option that should certainly be considered in the future, because if you think of circular gatherings that you might want to create to focus on a single object of interest. But for that opens actually up a very new research area now, where we need discordant teleportation techniques that are still like good for spatial awareness. So yeah, big shout out to everyone. We are looking for your contributions here.
Mm-hmm. Okay. There are lots of questions here.
Yeah, I can see it.
Yeah, you all should come and join us in the hub afterwards. So there's one by an anonymous person, which is a little bit maybe towards future work. Can you talk a bit about groups of more than 2 people?
Yes, absolutely. So this technique doesn't scale at all. That comes to no surprise to anybody. If I have now 5 users and have 5 rays going through the environment, that will be crazy, and I don't want to adjust like the position of 5 users on my touchpad. So no scalability given here at all. But the point we would like to make here is like really this framework idea and the idea of virtual formation adjustments in general. So if you want to, like in the future, look for techniques that involve more users, we would of course also need to think how we could specify virtual formation adjustments for groups. And one example that I mentioned already earlier would be, for example, such a circular gathering. That would be a reasonable formation that users would maybe want to generate. But there are, of course, more like just side-by-side formations, for example, or like just compact formations to fit through spatial constrictions. So yeah, again, a lot of future work to do here, and we are really happy that this sparks this sort of discussion here.
Yeah, exactly. It's a spark, and I think we see from Slido there's lots of excitement, just like for the previous talk. Also, great session we are having here, and let's all meet. And maybe next year, there will be lots more papers following you and citing you.
I would be happy about that.
Yeah. Okay, contact Tim directly also if you want more discussion about this topic.
I heard that the audio of the talk didn't work in between, so if you need the full talk, I can provide the video on Slack afterwards. So if you want to see like the missing audio parts again, I can provide that link. Thank you.
All right. So congratulations also to the previous talk, and let's move on to the third presentation in half a minute. Okay, there was a little bit of a
Thanks
break
for the
right now,
introduction.
but now we are ready for the next
Live from
talk.
Hubs,
This
I'm going
is
to
on
give you
the
this
space
talk about the
bender
paper
supporting
titled The
natural
Space
walking
Bender.
via overt
I would like to
manipulation in the virtual
thank
environment. It's done by a group of people from different universities: Adalberto Simeone from KU Leuven, Nielsen from Aalborg University, then André Senna from DFKI in Germany, Markus Speicher, and also Florian Daiber, all from DFKI in Germany. The presentation is given by Adalberto Simeone out of the hubs situation, and he is an assistant professor at KU Leuven in Belgium.
All right, thanks for the introduction again. Yeah, sorry, we are covering new ground, so some technical difficulties are to be expected. So welcome from in my hubs room for my talk about the space bender. Greetings from Leuven in Belgium. Again, I'm Adalberto Simeone, and we're going to talk to you about this newer locomotion technique that we have developed. So why we call it the overt manipulation? So before describing what we mean by overt manipulation, just a bit of a recap. So in a paper by Nelson et al., they have described various types of redirected walking techniques. So one category focuses on the manipulation of gains, such as translational, rotational, bending gains, and so on. But another category focuses on the manipulation of the environment itself. There are a few notable examples of this kind of manipulation of the environment. For example, in Change Blindness, a paper by Suma et al., the system uses this effect called change blindness to change the layout of the room after a person enters it. So as you can see from the picture, the layout changes after the person has entered it, so that the room from which they entered is no longer in the same position as when they are going to when they are going to leave it. In another example, also by Evan Suma, the system uses self-overlapping spaces in this technique called impossible spaces to reutilize the physical space available without the user noticing. And then yet another technique called flexible space by Vasileska et al. The system uses procedural generation to generate corridors in order to bring the user from a virtual room to another virtual room, but still in the same physical space. So these are, in literature, these are referred to as examples of subtle manipulations of the virtual environment. Subtle because the user is not expected, or it is not intended to be aware of what's going to happen to the virtual environment. So the changes happen without the user noticing. So by contrast, overt manipulation would be something that's visible to the user, that the user will notice when it happens. And indeed, there are very few examples. One of these is the paper called Mapping Virtual and Physical Reality by Son et al., which uses a constant type of warping of the virtual environment to adapt it to the physical layout of the room. So the user, as you can see from the picture, will see the virtual environment constantly being warped in their view in order to conform to the layout of the physical environment. So here comes the space bender. And as the name implies, the technique consists of a very simple approach in bending the virtual environment. And if the cameraman will now follow me to the video, the approach is very simple. So the user, this is intended for room scale environment. So the user is walking normally, and then at some point, like the chaperone grid will appear because he's maybe close to seeing close to a physical barrier. So with the space bender technique, basically we know when this is happening and we bend the virtual environment in order to allow them to continue walking. So in this way, the environment will follow the layout of the physical environment, thereby allowing the user to continue walking indefinitely. Okay, so there are a few things that we need to talk about in order to use this technique. So first of all, we have used, this requires the use of a special 3D assets. For example, the walls that you have seen in the video, they use this concept that in the 3D in Unity and Unreal terminology are called spline meshes. So basically, a spline meshes is a technique that uses one of these special assets that has enough vertices in the 3D object in order to allow it to follow the layout of a curve. So as you can see from the picture, there are 32 vertices on the side of the 3D object. So in this way, we can manipulate it so that it can follow a curve, for example. Indeed, this is what the final result would look like. For example, if we were to apply to a corridor, and then the bent corridor would look like this. However, it's bending a linear path, even this simple, is not trivial. Indeed, in order to create such a corridor, we need to calculate what in geometry is called a parallel curve. The optimal approach would be to use a 10th order polynomial, which is it's not very difficult, but it's neither it is very simple, because as you can notice from the previous slide, the interior curve is smaller than the larger one. It's not simply an offset. So basically, we calculated an approximation based on quadratic Bezier. And then you can download the implementation we have created on GitHub, which is available in the link over there. It was done with Unreal Engine and uses a C# plugin. So how does it work? In order to test it, we created a prototype implementation that is based on a linear corridor. In order to test it, we applied this technique on a corridor which follows the perimeter of the room, and we tested it in an area of 5 meters by 5 meters. Okay, so the algorithm is as follows. So basically, we have various sections. So the linear path that you have seen in the video and that we used in the test is a 100 meters path. So this was divided in various sections, each about 3.5 meters long. So there's a trigger at approximately in the halfway in each section. So when the person walks across this triggers the animation. This triggers the animation of the band, which follows the 90 degrees angle, and then this keeps happening as long as the user reaches a boundary. And so the process continues until the person has reached the exit that we use in the task using in the user study. So with the study, we wanted to basically test a few things. So first, we wanted to understand whether this approach does cause cyber sickness. Does this bending happening in front of the user's faces make the user sick? Or will user actually even use this kind of technique? Do they even want to use it? Is something that we can use in a real scenario, in a game, and a VR application to explore virtual environments that are larger than the physical space we have available. So we used various measures such as Kennedy's simulator sickness questionnaire, or we asked users which techniques among the ones we use they prefer. We had various questionnaires, we interviewed participants and so on. So, and also we wanted to understand whether this is an effective technique compared to other techniques that we could effectively use in room scale scenarios, such as resetting controllers that are typically used in these in scenarios where the physical space is not very large. And also compared to other de facto standard locomotion techniques that are used in commercial VR application or games, such as teleportation. So as an example of a resetting controller, we use this technique called freeze turn, which was originally described in a paper by Williams et al. In 2007. In this technique, it was required that the operator froze the frame basically, and then asked the user to reorient the user themselves. We tried to implement this at first, but during pilot testing, we found that there were some problems, and the fact that of freezing the frame made people a little bit dizzy, and so we made some modification to the technique. And here is our adaptation, which you will see in the video. So this is our how we changed the freeze turn technique. We call it the stop and reset technique. Basically, the user again, walks as usual until they encounter the chaperone grid, and then they press the trigger on their controller to teleport themselves in place. And when this happens, they are virtually rotated in place in order to continue walking. And we also used another technique, the teleportation, which is again basically just the stock implementation of that is available in the Unreal Engine. So they press the trackpad to trigger the teleportation, and then they will be virtually teleported in the location they've chosen. And we didn't change anything from the stock implementation in the Unreal Engine. As a task, we created this linear path that was 100 meters long, and users had to reach the exit using each technique. So we designed a user study where we had 13 participants who were male and 6 were female, and so 19 participants total. They were aged 20 to 39 years old. And they were all using the HTC Vive plus the TPCast wireless add-on, so that while they moved, they will not be hindered by cables. And they were all carrying one of the Vive controllers because in order to keep conditions equal between the study. But participants those who were using the space bender technique, they didn't require any form of input because the activation of the technique was used by walking across the trigger. So we did have a few differences in terms of starting conditions. So that's because participants who were using the space bender technique were facing as you can see, the direction indicated by the blue arrow, whereas the other two techniques, the direction faced by the purple arrow. This was because we originally thought of using the diagonal, because that would allow people to walk longer before resets. But in pilot testing, we found that people tended to drift, and this caused a variance in the length of the path that they were allowed to walk. So we decided to use the horizontal distance in order to keep things more consistent. In terms of results, as you can see from the chart here, we found that the space bender technique allowed people to walk faster in terms of walking speed than the other walking technique. Instead, you can see the people who use the teleport, they were not walking at all. They tried to walk a little bit, but as my colleagues described in the previous presentation, after a bit they stopped walking, just ended up teleporting. And also, if we look at the walking completion times in the walking techniques, the space bender allowed people to complete the task much faster. And we also saw some differences in terms of the actual length that was walked. Indeed, because like the geometry of an athletics track, Those who walked close to the inner edge were a bit faster than those who walked close to the outer edge. And so we recalculated the analysis on the average distance that people travel. So in fact, as you can see, people who were using the space bender technique walked about 10 meters fewer than people who were using the other technique who walked longer, specifically because of this effect. And so we recalculated the ANOVA based on this new distance, but we found that the space bender was still faster than the other techniques in both walking speed and completion times, at least if you look at the walking technique. And it was also much more efficient than the other ones. In fact, people could continue walking. They didn't need to stop because they could just slow down. And so participants spent just 2% of their time idling, so that barely moving compared to the two other techniques. It also caused much less drifting. As you can see from the picture, they were able to be kept in the virtual boundaries as compared to the other two techniques. In fact, people tended to drift, especially with the resetting controller. In terms of simulator sickness, we found a significant difference between the space bender and teleportation, because the participants using the teleportation were basically standing still. And in fact, from the chart, you can see that the results we got from the space bender are in line with the other studies reported in literature. So an average score was 16.53. And we also report a score for the other techniques. In terms of preference, although we didn't find a significant difference between the space bender and the stop and reset, we did find a difference between the space bender and teleportation. As you can see, more than half of the participants preferred using the space bender technique. So what does it mean for use in VR application? I want to remind that this, more than evaluate the performance and propose this as an alternative form of locomotion, we wanted to actually understand whether this form of overt manipulation of the virtual environment was a feasible approach. And we think that this is both efficient, but also something that can be used, because participants didn't find any major problems. They could just slow down rather than come to a full stop. In fact, some participants said that it was a more natural way of moving. People could keep walking and walking without ever having to stop. One participant even said we could actually run using this technique. In terms of presence, some participants said that they were significantly less aware of their physical position. We asked this question in a custom questionnaire, and they were surprised to where they found themselves after completing the task. And also, there were some issues with the other techniques. When using the stop and reset, participants had to abruptly stop because the short distance was enough to make them forget that there was a boundary there. So they walked, but had to gain some speed before actually having to stop when the chaperone grid appeared. And so, of course, it was testing a very simple scenario, and which was this 100 meters linear path. And so, therefore, the technique has some limitation. In fact, in the future, we want to apply this to more complex environments, but already in its state, we think it can be applied to indoor environments. For example, like many VR applications are set in FPS-like scenarios where people are exploring indoor environments. So the corridor could be mapped in the perimeter, just as we did in our study, and rooms could be mapped to interior areas. So if you imagine the corridor mapping to the perimeter, there will be an interior part of the room, which could be actually a room. So this means that if we are moving in a clockwise fashion, then the part on our right side will be the room. So this means that there will be a problem if the room that we have to navigate in is into the left area. But this could be solved, for example, by generating a 180-degree U-turn kind of bend, like in a flexible spaces approach. So people could reverse the direction, and this could be triggered by, for example, interacting on a door. And then people could have the available space on the correct side, in this case, for example, on the left side. It could also be used in its state to explore large outdoor linear routes. For example, if you were playing Skyrim or Red Dead Redemption, you could actually think that you could walk the distance from one city to another city by bending the route as needed. So the implication is that I think with the promising results we have found show that the overto manipulation of the virtual environment is a viable approach that can be actually used and that we will continue to work on in the future. We think this can work best in conjunction with other techniques as an alternative to resetting controllers when redirected working, conventional redirected working cannot be used as effectively in small spaces. But more importantly, we want to understand what you will design in terms of what new forms of overt manipulation will you design, because the manipulation of the environment with the bending of the geometry is just one example, but there could be many more opportunities, many more types of this kind of manipulation. All right, I hope I have not run over time too much, so or be short, too short. I don't know what happened. So yeah, if you have any question, I'd be happy to answer them in the Q&A session or in Hub afterwards. Okay, thank you. I will now go back to the traditional reality. Thank you for listening, and see you next time.
Okay, sorry, there were some more hiccups on the sound side. I will only take one question now, even though there are quite a few that have been posted in Slido. There's one that had a recurring theme by several people, and I think Doug brought it quite to a concise question. How would the user distinguish between bent space for redirection and an actual bend in the virtual corridor? Something about wayfinding. Several people asked about this.
Yeah, so basically the bending happens only when needed. So at some point they will know what the environment in the current state looks like. No? They knew that it was a linear corridor, and so the space would remain bent just for the duration of the person to change their direction and move to the bent area, and then it will restore automatically to the normal state. It will straighten out. So if they looked backward, they will see the corridor still being straight. So in a more complex environment, there will be a moment where people are aware of how the environment looks like in the normal state and how it looks like in a bent way. But of course, this can be made more apparent to user because we use a fairly simple environment, but we can use a more complex environment.
Okay, thanks for the great talk and the brave presentation in the hub itself, the way to go in the future. Let's go on with the next talk. Hopefully there won't be as much of a break in between. We'll see you in a Okay, so the next talk is on exploring effects of screen fixed and world fixed annotation on navigation in virtual reality. This is work done at Clemson University by James Dominic and Andrew Robb, and Andrew will be giving this presentation. He's an assistant professor at Clemson, and his research interests include consumer use of VR, human perception, presence, and self-avatars. Okay.
Hello, everyone. It's a pleasure to be with you all virtually. This is work that was performed by a master's student working with me, James Dominic. He's since then moved on to a PhD in machine learning, which is why I'm presenting today. So this work started out motivated by maps like this. So we've all probably been in hospitals, large industry complex that are very complex buildings and are very difficult to navigate for visitors, but also potentially even for people who work there regularly. And so we begin wondering, what would, say, a Microsoft HoloLens combined with Google Maps look like in this particular context? And so we'll be talking about a few research questions. First is, how do annotations influence locomotion and navigation behaviors? So essentially, what is the virtual information being displayed, or the appearance of the virtual information? But we also want to think about what type of information should be displayed, or what amount of information should be displayed. And then we're also looking at how the annotation type interacts with the information actually shown. So one note here, we talk about this in an eventual AR context. We are piloting this research in a virtual reality headset because it gives us a lot more ability to control the actual environment that people are moving through. So we had 48 participants in our study. 38 were male, 18 of which actually dropped out due to sickness. We'll talk more about this later. So we had 30 in total. These participants were recruited from a VR class, so they were familiar with the technology. So we're looking at annotations and information, and so we designed a 2x3 repeated measures within subject study. So we have two types of annotations, which I'll show you in a second, as well as three what we'll call levels of information. We'll also see examples of those in a second. Participants completed 3 trials for each possible combination, which led to a total of 18 trials. Each trial took about 1 minute to complete. And during these trials, participants were navigating to a specific target destination. So we generated 18 unique floor plans. One was used for each trial. And each of those floor plans looked something like this map you see here. So we have a large space which has several clusters of tightly connected smaller rooms, and then these clusters are connected by larger hallways. Participants started in random locations and moved to a random destination with the constraint that both the starting point and the destination were in separate blocks and were also on different sides of the map. So they were navigating across the entire space. We also gave participants a secondary task during the experiment, where here they were being asked to put out fires that they encountered while traveling to the destination. And so they're taking on the role of a firefighter moving through this building, trying to reach a specific destination. And then once participants reach the destination, we ask them to point back at their starting location so we could get a sense of their spatial memory. The one last note that's important here, so participants were moving using arm swinging, an artificial locomotion technique. We implemented this using VRTK 3.3 Virtual Reality Toolkit. The space that they were moving through was much larger than we could do in real life, given the tracked environment we had. So we used this as a substitute. So let's look at the different types of annotations we have. So there's two types of annotations. The first class was what we'll refer to as a screen fixed annotation. And so we could talk about this as a heads up display, or if you imagine Google Glass, you have some information which is shown in a fixed part of your visual field. So we're just seeing a portion of what users are seeing here, but in the upper left corner of their vision, we have this mini map, which is floating in space. And information about the space is being conveyed on this mini map. It's always visible to the user in the upper left corner, positioned such that it's relatively easy to look at, but isn't obscuring the main field of view. In comparison to this, we have world fixed annotations. And so now, rather than always being visible and based on in a view dependent position, based on the user's gaze direction, we now have annotations that are spatially located within the world. And so here we've got an example of annotation we'll talk about in a second that's showing the walls or the floor plan of the space. And as the user moves around, these lines remain in the same spatial location. So two types of annotations. We also have three levels of information. So we have our destination marker is our lowest level. It's only showing you where to go. So it's a little hard to see in this picture. We have an icon here in the corner, which is the direction the user should be moving in. Next, we have destination plus walls. And so now they're given some floor plan information in addition to the destination that the user needs to head to. And then finally, we have a destination plus path. And so now we see the destination where the user is heading and the path that leads us to that position. Note that these are not additive in that walls are not visible in the path. And so they all have destination visible because otherwise the participant wouldn't know where to go. But otherwise, we're looking at these as completely different representations. And so we can see all six shown here. We have our screen fixed, all mini-map based destination, walls plus destination, path plus destination. Then we also have our world fixed. You have only the destination. It's visible through obstacles. Our walls plus the destination. The destination is not visible in the screenshot. And then our path plus destination. And so here, the user is very close to the destination until we have a larger marker. You can also see an example here of one of the fires participants were looking for. So we're interested in how this affects navigation and locomotion. And so we're looking at several metrics related to this. First, time taken to reach the destination. We're also recording the total distance traveled in the virtual world, looking at how many secondary tasks were completed, and we're also recording the shortest possible distance. And so this was computed using an A-star algorithm and tells us what the distance of an ideal path would be so that we can look at how participants deviated from this path. Then we also had several surveys looking at demographics before the experiment, simulator sickness, presence, and user preferences after the experiment. Before we jump into the results, I want to talk about some pre-processing of the data. So each trial was randomly generated, and that meant that the actual path distance participants traveled during each trial was different between conditions and between trials. And so to help control for some of this variation in our analysis, we normalized metrics based on the shortest possible path or some other value. And so in particular, we took the actual time taken, normalized it by the shortest possible path length, so that this was scaled based on what is sort of a realistic shortest possible time for their given path. We did the same thing with distance traveled. Total distance traveled was normalized against the shortest possible distance. And so we now look at a ratio between these two values. And the number of secondary tasks, we normalized it based on the actual distance that was traveled. And so the reason we're using actual distance here is that the tasks were randomly scattered throughout the space. And so the number of tasks that participants encountered depends and changes based on how far they actually traveled. We analyzed the results using linear mixed methods. We had annotation type, information level as our main fixed effects. We also included simulator sickness in our model since we had such a high sickness response. And we included normalized number of secondary tasks since that could influence the time taken as participants stop to put out a fire. And I'll leave you to the paper for the rest of the statistics. Okay, so let's actually talk about our results. So first, with time taken, we found a main effect for both annotation type and information level. If we look at this graph here, we have our annotation type encoded via color and our information level encoded here. And so we are seeing many significant differences. In particular, some interaction effects we observed that I'll highlight specifically. We see world path, so world fixed using the path is performing better than screen destination and screen walls here. We also did observe a trend for sickness that was close to significance, but not quite, which suggests that sickness may have increased the amount of time taken to travel. With distance traveled, we're seeing similar effects, though not quite as strong. We have a trend for annotation type, p-value 0.057, and a main effect for information level. Significant interaction effects we're interested in here. World path, again shown here, is better than screen destination or screen walls. We also see here screen path is better than world destination. We'll come back to this when we talk about in our discussion. And we found no effect of sickness on distance traveled. So sickness may have affected time, but it doesn't appear to have affected distance. We can also look at speed, how quickly participants were moving here. Again, we found main effects for annotation type and for information level, and a significant interaction effect. And in particular here, the interaction effect we're seeing and the main effects are being driven by people moving more quickly in the world path. So you have a world fixed annotation showing a path to the destination. People moved more quickly in that condition. We also again saw a main effect for sickness where increased sickness reduced speed of travel. For spatial memory, we did not find clear significant effects here. There was a trend for annotation type, but there was no effect for information level, and there were no significant interaction effects. We can talk about this a bit more later, but in a nutshell, we think that the environments we had people traveling through were too complex for people to build a strong memory of due to those smaller clusters of rooms that were very intricate to navigate. For secondary tasks, we also didn't see any effects here. No main effect for annotation type or information level. We did find a significant interaction effect, but in post hoc, there were no significant differences between any individual comparisons, which makes this a little bit difficult to interpret. And then final results before we talk about sickness. We asked people to report a preference on a value from 1 to 5 for each of the interfaces, and so these were scored independently. We analyzed this using a non-parametric Friedman test and found significant differences. Post hocs revealed many different significant differences, and we report these in the paper. But the pattern that emerged, and what I want to mention here, is that changes in preferences were driven by information level, not annotation type. And so if we look at the graph, we can get a picture of this. We have screen fixed destination, world fixed destination, screen fixed walls, world fixed walls, path for both. And we see that differences in annotation, but the same information level show very similar patterns. And so for destination only, we have a low score. For walls only, we have medium to high. And for path, we find medium high to very high. So let's talk about sickness. We had a high dropout rate for this experiment. We did find a significant difference in scores for people who dropped out versus who completed. Here we have in red people who did not complete the experiment. In blue, we have people who completed it. And so we do see that people who completed the experiment had much lower sickness scores, and this is the only data that was included in our analysis. We did not include any data from people who dropped out of the study. As to why this happened, we think this may have been due to a combination of using screen-fixed annotations and a partial gait locomotion technique, both of which are known to individually contribute to increased sickness. All right, so we'll wrap this up. Takeaways. So we see that both annotation type and information level is affecting performance. Generally, users perform better when using world-fixed annotations, and generally, you find that path performs best, then destination, and then walls, but this is a less clear pattern from the data. But more important than that, we see that there's an interaction effect between annotation type and information level. And in particular, we find that world fixed plus path is outperforming almost every other condition on most metrics. We can also see from our data that it's important that you get the right combination of annotation and information. And so world fixed is not necessarily always better than screen fixed. We had a measurement earlier when we're looking at distance traveled, where world fixed plus destination performed much worse than screen fixed plus path. And so here, even though world fixed is overall better, we find that a screen fixed system performs better due to its particular combination of annotation and information. And finally, we saw that user preferences were primarily driven, surprising to me, by information level rather than the mode or the annotation by which it was actually presented. And with that, thank you very much. I'm happy to take questions.
Are we ready? Are you counting down again? Okay, thanks, Andrew, for this also very fascinating talk. And again, we have some questions lined up. Let's go quickly. Bernhard Ricke says, interesting work. Any suggestions or insights on how the results might transfer to real world situations where people physically walk and environments tend to be more complex and queue-rich?
Yeah, excellent question. So so we used a call it a smooth or continuous locomotion method here. So arm swinging, you're swinging your arms to move, and an attempt to make our results more applicable to the real world where you have continuous travel. We would love to do work like this in the real world with an augmented reality headset. I think that we won't find that there will be significant differences due to locomotion or due to motion in the real world, since we're using a similar continuous technique here. With regard to complexity of space, that's an excellent question. And I don't really know if we can make strong inferences here. We were working with a very complex space here. And so I think that you would see similar patterns emerge in real spaces.
Okay. Thanks, and also thanks for the talk again. I think for the sake of time, we'll move on to the last talk in just a second and have more discussions then in the hub afterwards. Thanks a lot for your presentation.
My pleasure.
Okay, we are ready for the last presentation. It's on the magic carpet, interaction fidelity for flying in VR. And this was an invited TVCG paper, which means it's not directly submitted to the conference, but rather was already accepted and presented at TVCG. So you will find the text not in the proceedings, but rather in TVCG directly. So this is work done by people at in several universities, by Daniel Medeiros from University of Wellington, Antonio Sousa from University of Lisbon, Alberto Raposo, also from University of Rio de Janeiro, and Joachim Roche, also from Lisbon. So go ahead. Oh no, this is presented by Daniel, and he's a postdoc researcher at the Computational Media Innovation Center in Wellington, in New Zealand, and his interest includes mixed reality, 3D user interfaces, human-computer interaction, and locomotion techniques. It's all yours, Daniel.
Okay, thanks for the introduction. So my name is Daniel Medeiros, as you saw, and just let me do something here. So yeah, and I'm here in New Zealand at 5:30 in the morning, and I'm, as Gudrun said, I'm here to present my paper, TVCG paper, and this work what have been done in the scope of my PhD thesis at the Instituto Superior Técnico University of Lisbon. So as VR gear has become more widely available, effective travel techniques have also risen in importance. Travel or locomotion is the act of translating people from one point to the other in the virtual scene in a given direction. It's also the most common and universal interaction task in 3D user interfaces and often supports another task than being an end in itself. This includes actions such as selecting, manipulating, and interacting with objects in the 3D scene. To evaluate travel, Bowman et al. Proposed quality factors which includes ease of learning, spatial awareness, appropriate use of speed, accuracy, and presence. One of the main classifications for travel techniques is by task decomposition, which separates travel phases by the act of indicating direction, controlling speed of movement, and input conditions, which indicates how the movement is initiated, continued, and terminated. A way to approach travel in VR is by addressing it with fidelity, which is a concept which relates to how close real-world sensory stimuli are reproduced. So, and when dealing with the way people interact, this concept is called interaction fidelity. So the higher level of interaction fidelity a travel technique has, the closer it is to the way people walk in real life. Work by McMahon et al. Shows that the use of a high interaction fidelity technique, such as the human joystick, which emulate the joystick but using people's bodies, can improve efficiency when using VR technology. However, objects may reside out of reach and in remote locations of the virtual environment, and natural metaphors alone are not sufficient to support travel. In these cases, users may need to use flying metaphors to reach these spots. So, but one of the problems with this type of approach is the unnatural control of multiple degrees of freedom to support locomotion. Some attempts of flying is by using machines such as a paraglider, a spaceship, a zero-gravity simulator, or Birdly, where the user fly by flapping their virtual wings. However, the use of such equipment limits users' action to the action of traveling, which may not be suited for complex virtual environments where users need to perform further actions, such as object selection and manipulation. One example is the work by Wong et al. 2012, who uses a balance board to control flight in virtual environments. However, the use of leaning to control direction of flight led to 25% of the users to quit the test due to severe cybersickness side effects. Another example is a work by Boma et al., 1997, where the authors explore techniques that use indicated direction using their heads or hands and found similar results for both techniques. However, results are still preliminary as the virtual environment used did not include any obstacles and users were not able to see their own bodies. We argued that the decoupling between direction indication and speed control travel phases enable to isolate the unnatural part of travel of flying, which is the control of the 6 degrees of freedom, enabling the use of high interaction fidelity techniques for speed control, which can improve the effectiveness of the flying experience. So when using high interaction fidelity techniques in VR, Users need to be fully represented by an avatar in the virtual environment, as the users needs instant feedback. The use of an avatar also makes it easier to people locate themselves inside the virtual environment and affect their space judgments. So in this paper, we evaluate how interaction fidelity influence quality factors such as efficacy and spatial awareness on flying travel tasks. For that, we developed the Magic Carpet design space, which combines a fully embodied representation with a floor proxy to avoid imbalance issues. This design space enables the use of high interaction fidelity techniques, metaphors of flying. To assess the best performing techniques on both direction indication and speed control phases, we conducted 2 separate studies, one for each phase. The best performing technique on the direction indication phase was then used as means to indicate direction on the speed control study. So in this study, we used an Oculus Rift DK2 as an input device and 5 Kinects to provide body tracking, which are merged into one coordinate system using the Creepy Tracker toolkit. We limited the carpet size as a subset of the available tracking to provide a reliable tracking space. We used an abstract mesh avatar on the first-person perspective, and this avatar was used for both male and female participants. This avatar representation was selected as an abstract avatar as an output of the study presented on the paper Keep My Head on My Shoulders at ACM VRST 2018, which indicates that the graphical fidelity of the avatar in the first person does not affect that much travel quality factors in the first person perspective. So in the first study, we recruited 18 participants, and 2 of which were female. The age of the users varied from 21 to 35 years old, and 30 participants had previous experience with VR. We implemented 3 different techniques for direction indication, and on all of the techniques, the speed was limited to 3 meters per second, which was the speed to isolate the direction indication phase and not induce cyber sequence effects. And also a wand was used to trigger movement. The first technique tested was a novel technique called elevator per steering, which is the degrees of freedom separated strategy to control direction, which is a common approach in mid-air manipulation techniques to improve precision, such as used in the work by Mendes et al. On this technique, the direction indication on the horizontal plane is controlled by the projection of user's gaze on the horizontal plane, and additional buttons were used to control direction on the vertical plane. On the gaze technique, people control their direction using the direction of their heads, and on the hand technique by the orientation of the user's hands. And due to Kinect's limitations, we attached a reflective rigid body to be able to track our 3D wand using a 12 OptiTrack Flex 3 camera rig, and this was mapped into the user's dominant hand. To guide users through the scene, we positioned rings to indicate the desired path. Only one ring was shown at a time, and once crossed, successfully or not, that ring disappeared and a new ring appeared in a predefined location. This test consisted of 22 rings along a path with a length of 180 meters and included abrupt changes in the Z coordinate. To compare the technique, we used the metrics time, collision time, number of collisions, path length, and 6 Likert scale responses for subjective metrics. For the continuous variables, we used Shapiro wheel test to assess data normality. Because the samples were not normally distributed, we used the Friedman non-parametric test and Wilcoxon sine ring stats with Bonferroni corrections, which were also used for the questionnaires. So in the results, we found that the elevator plus steering technique had the worst results in our tests. It was the least efficient technique in terms of total time because the users spent most of their time colliding with objects. It was also the technique with the longest travel distance among the 3 tested techniques. The result for the gaze and the hand-oriented steering techniques were similar to those found by Bowman, where the gaze technique had the advantage in terms of the distance traveled and the hand advantage in collision time. Additionally, users indicated that the hand technique allowed them to be more aware of the presence of a virtual body, which corroborates with the shorter amount of collision time. The participants also found it easier to indicate the direction of movement and to navigate in the virtual environment using the hand technique as indicated by the questionnaires. So another advantage of the hand technique is that it enables the decoupling between movement and camera control, enable him or her to inspect the virtual scene while traveling. So we can indicate that the hand technique was the best performing technique to indicate direction in our tests. So in the second user study, we assessed the impact of the interaction fidelity for controlling speed when flying in virtual environments. The test design and methodology used in this test were similar to those in the previous study. In this study, we also recruited 18 participants, and 2 of which were female. And the age of the users also varied from 21 to 35, and the majority of them had previous experience with VR. We also used the same virtual environment and presented a test similar to that in the previous, but following a different path. This path was longer, measuring 330 meters, and contained average changes in the Z position. We also incorporated more complex maneuvers, such as U-turns, to force users to carefully control their speeds while they flew. As a result of the previous study, we used the hand technique as the means to indicate direction, and the upper limit speed was 5 meters per second. And this study, we tested 3 different techniques for speed control. So the joystick technique, where the speed was controlled through the analog joystick. And in this technique, we just included movement in the positive axis of the analog stick. We also used 2 different techniques with a high level of interaction fidelity technique. The speed circle, which uses the human body as a joystick, which was inspired by McMahon et al. And this technique uses closer to the border of the circle have maximum speed. So we rendered an additional circle in yellow to prevent users from stepping outside the circle when reaching the maximum speed zone. The circle was divided in positive and negative halves, which are updated according to the user's orientation and position in the circle. Only when users were on the positive half of the circle, they were able to control speed of movement. This feature makes the movement to stop when making abrupt movements such as U-turns. People could prevent this by moving their body while traveling or by walking forward in the circle when the movement stopped. To avoid this, we explained this limitation before users performed the training task, and I asked them to perform these maneuvers during the training task. And last, the last technique we tested was the walking in place, which emulates the action of walking but remaining stationary. So to compare the techniques, we also used the metrics time, collision time, number of collisions, path length, speed variation, and 6 Likert scale questionnaire responses for subjective metrics. We also use similar statistical tests as the other ones, but with repeated measures ANOVA and normally distributed data. And so as a result in our test, we noticed that users experience more difficulty in coordinating the direction indication and speed control phases with the walking in place technique. Consequently, they had more difficulty to control speed as more participants stopped the speed control movement when they reached the ring, then pointed to the next ring and then flew to it. With that, these techniques, users also felt more cybersick. And regarding embodiment, users felt less control over the virtual bodies with the walking in place. And this may be attributed to the noise and the depth sensor signals. Another interesting point reported by the participants was that they lost balance in some cases because of the weight compensation that occurred naturally during their gait in real life, for which the emulated experience did not entirely match the actual experience. So with this, we can infer that the walking in place was the least suitable technique in terms of task performance in comparison to the other, but still efficient. The joystick technique was found to be generally the most efficient technique for flying in immersive environments. And this may be explained by the familiarity the users already had with video games. However, in most cases, the user did not finally control the speed as indicated in the figure, but instead maintained the maximum speed of most of the time. We can also report that the joystick rotation did not induce increased cybersickness in flying tasks as opposed to room scale VR. The speed circle was not the most efficient technique, but in the technique, they had a more precise control of speed, as we see in the figure, including the abrupt movements. And people also pointed that more training could improve their performance with the speed circle technique, as people reported that they got lost in the circle, but quickly compensating by recentering themselves. They also stated they needed to periodically look down at the circle, which affected a little bit their performance. So previous work indicates that high interaction fidelity techniques can translate into quality factors in ground constrained scenarios when VR technology is used. But we found that interaction fidelity does not always translate into quality factors in flying tasks inside our magic carpet space. So although the joystick technique has been proven optimal for use in such an application based on our tests, we can still identify the speed circle technique as a good alternative when more precise speed control is required. So in this paper, we can conclude that we designed and validated our magic carpet design space. And we can say that this design space is indeed an effective way to fly in VR, enable the use of high interaction fidelity techniques for flying by decoupling the unnatural control of multiple degrees of freedom and then addressing the speed control with high interaction fidelity techniques. So inside a design space, we can notice that high interaction fidelity can improve quality factors, especially when a more precise control of speed is needed, but this kind of technique not always translate into quality factors. So with our design space, this leaves us with the opportunity to explore the magic carpet by using state-of-the-art techniques for travel, or even propose novel techniques for flying inside the design space. So finally, I want to thank everybody involved in this work and everybody that is seeing the talk around the world. Thank you. Now I'm open for questions. Thank you.
Okay, thank you also for Daniel for this fascinating flying experience. And please send your questions to Slido. We have one question right now about how was the implementation quality of the tested techniques controlled?
I didn't understand the question.
How was the implementation quality of the tested techniques controlled? I also had personally a question there. You have two kinds of tracking systems, one with 5 Kinects, the other one with an OptiTrack system, and you reported all kinds of issues about the quality of the tracking with the Kinects. So maybe that's related to this question, saying, like, how did you test for this? And I personally wonder whether, for instance, the walking in place was partially hampered by the poor tracking quality of your system.
Yeah. Yeah, in our case, the tracking quality was already evaluated in the Creepy Tracker toolkit, which was a toolkit that was evaluated and published in ISS 2017. So we did all this kind of tests for tracking quality and everything. And in the terms of matching the two tracking spaces, basically we just used the rotation of the wand to map the rotations using their hands, just because the Kinect didn't have tracking for the hands.
Yeah. Yes, and I assume that since you use the Kinects mainly for position control and then for controlling direction or orientation and also speed, you use the OptiTrack. So maybe that didn't really have too much of an influence, but it also may depend on the speed of the person's actions, how quickly they wanted the feedback from motion or speed changes.
Yeah, like I said in the presentation, like the walking in place ahead, that's why I mentioned the quality of the depth sensors. So if you have something that is, because we also had in the other paper that we mentioned, keep my head on my shoulders, we did the evaluation with real walking and it was good, but it seems like, for example, in the walking in place, there is like an emulated experience. People were expecting more. So you have kind of an uncanny valley in terms of like interaction fidelity and like expected motion and the actual motion that people are doing.
Okay, I'll close with one final question by Steve Feiner, that just came in. To avoid the need to look down to see the circle, did you consider raising its visualization, perhaps making transparent and visible only on demand?
Oh, what the circle itself? Well, we kind of think about it, but one of the participants said it was really good. But it was not a. It was more like an idea of their physical representation and their like virtual representation. And also, people really report like the idea of the circle because like one or two people had like fear of heights, and was also one of the ideas of the speed circle technique, like the magic carpet technique. So for example, if you people it just kind of looked down a little bit and they were like, oh, okay, I'm here, i'm 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 controlling the speed, so I'm okay. I will not fall down.
Okay. Okay, so thank you again for your presentation as well. And before going back and forth to the conference room, let's finish this session with, I would like to thank all the speakers again for really fascinating presentations and also audacious presentations in the hub and with video, etc. I also really want to thank the coordinator, Andrew Rukangu, who is working behind the scenes, and he and his colleagues, they're doing a marvelous job, I think. I was really stressed out by just this little bit of communication I had to do here. They do this now continuously, like session after session. Great job. And besides that, thanks to the audience for so many questions that you all put into Slido. It was really exciting, and I feel like being part of a worldwide community, seeing all this this communication happening here. And so that's a great conference. And maybe for further discussions now, let's go to the hub. I just posted the room name. It's the viewing room 2, the large room, and I also put the URL in our into Slack, into our session 19 part of the Slack. So I hope to see you all there very shortly. Bye.